All right, questions? Any questions? We have a test on Tuesday over chapter 8. So if I were you, I would work ahead on the homework and just make sure that you've kind of shored up your understanding in terms of all the things that we did there. Again, the last thing that we did was in chapter 8 was improper integrals, the application of L'Hopital's rule there. That does come up from time to time when you are dealing with those improper integrals. And the last integration topic that we did in terms of new information, in terms of doing integrals, integral techniques would have been the partial fraction decomposition stuff, yes? Okay. And last time we started talking about sequences, okay? And we talked about, really informally, these things are just ordered lists of numbers, yeah, ordered lists of numbers. So we can talk about the terms of a sequence, and we can talk specifically about which term we are referring to. So we can say the third term or the fourth term in the sequence. Okay, so if you see this sequence right here that I have listed 3, 7, 11, 15, etc. If I said the third term, you would all know what I mean, right? It would be which number? 11. Yeah, so that would be the third term. That would be the third term in the sequence, okay? So, and we gave a name to that, A sub 3, remember? Okay? So in the end, what we realized was a sequence is really a function that has as its input its position in the sequence. Is it position 1, position 2, position 3, etc.? That's the input. And the output is the actual number that appears in that position. Yes? So don't go crazy trying to sort out what is this function stuff. It's simple. It's supposed to be simple. The input is the number, like which position it is in the sequence. The output is the actual number itself, yes? So the output in this case is 11, and the input is 3, because we're talking about the third term. Okay, so a sequence is a function from the so-called counting numbers or natural numbers to just the real numbers, okay? We introduced the notion of factorial last time, factorial. So for instance, 5 factorial, right? What is that? What do I mean by that? That's 5 times 4 times 3 times 2 times 1. We also realized, by the way, that's 120 as a number. But we also realized that this is like 5 times 4 factorial, right? Okay, because it's 5 times, and then you just go 4 on down. And that would complete the 5 factorial. Okay, that's convenient to sometimes peel off like the first or second of a factorial, and then just leave the rest of it right there. And sometimes you'll be able to cancel some stuff. So the first thing I wanted to do, remember we talked about how sequences will sometimes have formulas, like you'll write A sub n, okay? So like, expressions, you might write like A sub n equals what? Like what is the nth term? And sometimes you have to think in terms of patterns that are emerging, yes? So for instance, for this guy right here, what do you have? You have like A1 equal to 3, A2 equal to 7, A3 equal to 11, A4 equal to 15, and you want to discern some patterns here, right? And one pattern that I would submit to you is that the way that we're moving to the next term is by doing what? Adding 4. That is usually a good strategy, is to say, okay, am I adding something? Am I multiplying by something, etc., right? You're adding 4 each time. And the goal is, what is the formula for A sub n? Like, do I have to just, for instance, if I asked you for A sub 37 trillion, it would be really annoying to have to like keep adding 4 to itself 37 trillion times. You know what I mean? So it would be much more convenient if I could just write down a formula and straight up plug in what n is and immediately know what A sub 37 trillion is. Yeah. Okay, so what I want to do is just turn you loose for, I don't know, 10 minutes or something, and try to come up with formulas for each of these sequences. Write down a formula for the nth term of each of these sequences. This is an exercise in pattern recognition, okay? So I want you to work on these guys right here. It's kind of a first in-class exercise. So go for it. All right, let's talk about this. Okay, so again, you're trying to make an expression that depends on the term you're at, right? If indeed this is a function from the counting numbers to the real numbers, then there ought to be, in theory, a way that you could write down a formula in terms of n, the term that you're on, that would kind of give the sequence. Like it would tell you like what term should be at the trillionth position in the sequence. So what did you come up for the first one? Okay, so for this one you had A1 is 3, right? A2 is 7. Okay, what was the formula that you came up with? AN equals what? Anybody come up with one? Yeah.
This might be way overcomplicated, but -1 over n times n plus 4n. And it works.
Oh, whoa. Okay. Why do you have -1 over n? Why does it -1 over n times n? Why don't the n's just cancel?
Well, cut in. Okay, so for example, the first value is -1 times 1 plus 4 equals 3, and then -1/2 times 2 is 1. A equals 7.
Oh, I see. Well, yeah, there is an easier way to express it.
Yeah.
What's that? I don't think that all of those are one less than a power of 2. Just 4n minus 1. It's 4 times the term minus it. Look, so like the first one is 1 less than 4. Does that make sense? This is 4 times 1 minus 1. Yes? What's this? Think about it. And that makes sense because to go from one term to the next, what were we doing every time? Adding 4. So the next one, look at 7 is 1 less than 8, which is 4 times what? 2. Okay. What about A3? So 4n, or sorry, this is 4 times 3 minus 1. Yes? Etc. So you see that this is working. It's always just 4 times whatever term you're on. It's 1 less than 4 times whatever term you happen to be on. So 15 is 4 times 4 minus 1. Yes. Yeah, so this is absolutely equivalent to just 3 plus 4 times the quantity n minus 1, for instance. Or what you're saying is an is like an minus 1 plus 4, right? So the current term is the previous term plus 4. That's kind of what happens every time, yes? Okay. But either of these are ways you could write this. But if you were to distribute this 4, you would see that the one sort of simplifies to the other. Yeah. All right, questions on that? So that was just a matter of kind of saying, okay, what does it mean to like add 4 every time? Well, basically, it has something to do with taking 4 times the term that you're on. Okay. So what about the next one? Here, I'm gonna actually write down these formulas. Okay, so for this guy, it was an equal to 4n minus 1. Okay. What about the next guy? By the way, let me just write this. This is like 2 over 1, just to be more clearer. 3 over 3, 4 over 5. Do you see what I'm saying here? 5 over 7. Sometimes it's helpful to look at numerators and denominators separately. Do you know what I mean? So the numerators go 2, 3, 4, 5. Clearly the pattern's pretty clear there. That's always 1 more than the term you're on, right? How do I express 1 more than the term I'm on? What would I say? Yeah, so an is, okay, so first of all, the numerator is just 1 more than the term I'm on. Now what about the bottom? The bottom, you see, are the odds, correct? Yeah, it's right. So odds are always expressed as 2 times something plus or minus 1, right? It's always 1 less than a multiple of 2 or 1 more than a multiple of 2. We have to tie that to the term we happen to be on. And in this case, it looks like 2n minus 1 actually works, doesn't it? Check it out. Like if I plug in 1, does it work? Plug in equal to 1. It's going to be 2 over 1, which is 2. Yeah? Plug in 2. You get 3 over 5. Hang on. Wait, if I plug in 2, I get 3 over 3. Yes? Plug in 3. I get 4 over 5. Yes? It works. Great. Now this one, okay, so any questions on that? That's how that one works. Again, just doing some pattern recognition here. Yeah, what about this next one? The hint I gave is that there's a number you can multiply by to go between terms, yes? What is that number, Michael? Yeah, negative 2/3 is the way you move from one number to the next, yes? Okay, because think about it, I'll write it up here. So negative 1/2, 1/3, negative 2/9, 4/27. And what's going on here is you're multiplying by negative 2/3 every time. Every time. You're multiplying by negative 2/3 every time. Do you see it? Look, what's negative 1/2 times negative 2/3? A third. Yeah. What's 1/3 times negative 2/3? Negative 2/9. Yeah. It works. So that should give us a clue as to what an is going to be. Did you come up with something, Michael?
Yeah, I got negative 1/2 times the quantity of negative 2/3 to the n minus.
Yeah, right. Negative 2/3. The multiplication by negative 2/3 doesn't happen with the first term. Does that make sense? That only starts after the first term. Yes. So to get to 2, I would multiply by negative 2/3 for the first time. Yes. To get to the third term, I would multiply it by negative 2/3 for the second time. You see what's happening? The number of multiples of negative 2/3 is always 1 less than the term you're on. Yeah? The number of times you're multiplying by negative 2/3 is always 1 less than the term that you are on. So it's negative 2/3 raised to the n minus 1 less than the term you're on. N minus 1. Okay? Okay, cool. Let me ask you a question. I haven't asked you about convergence or divergence of these things yet. What about the first sequence? This one right here. If I took the limit as n goes to infinity, what would happen to that sequence? It would diverge to infinity, yes? What about the limit of this sequence? Would that converge or diverge? Converge where? 1/2. You could do L'Hopital's rule, or you could remember stuff about rational functions to sort that out, yeah? Okay. What about this guy? Oh man, that's just crazy. What about that thing? It goes like this. It kind of oscillates, but the thing is, you're also multiplying by basically a factor of 2/3 every time. I know there's a minus sign in there. Yeah. But the 2/3, what is that doing to the overall quantity in the end? It's shrinking it. Yeah? It's basically taking 2/3 of the previous amount every time, and hence it's going to shrink this thing down, and this thing is going to go to 0. Yeah? So let me just say that, that goes to 0. What about this guy right here? What about that guy right there? What's AN here? Oh, interesting. Okay, I'll give you a hint. The numerator is always 1. Okay? The denominator of the first thing is 1. The denominator of the second thing is 2. The denominator of the third thing is 6, which is 3 times 2 times 1. Yeah, it's factorial. It's the factorial of the term you happen to be on. So what's the formula? AN is 1 over n factorial. Now, what do you think about that? What do you think about that sequence? What do you think that tends to? Does it converge or diverge, or what's going on? That converges to 0 like really fast. Okay, because remember, n factorial just blows up like crazy. Okay. And finally, what about this junk right here? Okay, AN equals, okay, so first of all, you have an X to worry about. Okay, so it's like, it's going to be X to the, now think about it, the X was raised to the 0 power on the first term. X was raised to the 1 power on the second term. X was raised to the second power on the third term. So if I'm on the nth term, X is raised to the n minus 1 power. It's always 1 less than the term you're on. Now, what do I do about the other junk? Yeah, Benjamin. Yeah, it's like the factorial. This is like that. I was trying to see if you would remember that 0 factorial is defined to be 1. Yeah? So it's always the factorial of 1 less than the term you're on. Okay, so it's x to the n minus 1 over n minus 1 quantity factorial. Remembering that 0 factorial is 1, which is also the same thing as 1 factorial. And then it starts getting more interesting once you get beyond that. Okay, convergence of that isn't so clear. Well, or is it? Well, that's something we're going to have to look at later on. We need to know exactly how fast n minus 1 factorial is growing. The other thing is x, where x is some number. Does that make sense? X could be 70 for all we know. X could be pi, could be 1. X could be 0, right? And so convergence of this thing is going to depend on what x is, potentially. Yes? Well, that's something we'll look at later on. Yes, Daniel. Right, so x is a variable. Yeah, x is some kind of constant that is yet to be determined. Yeah. The reason I'm showing you that is that will come up later when we start looking at series. Yeah. The answer to that question is no. Any constant to any power is always going to grow much, much slower than the factorial function. Factorial function, so like x to the n minus 1, that's basically like exponential growth, which everybody talks about how massively fast that is, right? Exponential growth is a good thing in finance. You're like, oh man, yeah, I'm making all this money. Population growth, exponential growth, people talk about that all the time, right? But factorial growth, it just blows that out of the water, okay? So it turns out that if I did take the limit of this thing as n goes to infinity, no matter what x is, I'm always going to get 0. Because the factorial is just going to overwhelm what's happening in the numerator. Yeah. There would be sort of an initial kind of, it might go up a little bit, but then it would just plunge to well, of course, the graph would slightly depend on what x is, because x could be negative, for instance, right? In which case it would kind of go like this. It would oscillate like this around the x-axis, but then it would settle down to 0 eventually. The factorial will just absolutely overwhelm whatever x to the n minus 1 is. Okay? Factorial growth is massive. In fact, you know, let me just write this up here at the top. So in terms of growth rates, here's like the hierarchy of growth rates. Log is dominated by polynomials. Okay, so polynomial growth is much larger than logarithmic growth. Is smaller than, okay, what do you suppose is going to dominate polynomials in terms of growth? Exponential. And that, my friends, is dominated by what? Factorial growth. And there's other growth rates beyond that. You could take factorials of factorials. And that gets real gnarly, real quick. Okay. So there you go. Okay, any questions on that? So I mean, those are kind of, that's the hierarchy of growth rates. Logarithmic growth is dominated by polynomial growth, which in turn is dominated by exponential, which in turn is dominated by factorial growth. That's just a good kind of hierarchy to have in mind, though. Any questions on that? Yeah.
Do you have any good system of how to find these n equations and how to break down each one?
Well, the key is to think about how you move from one term to the next. So like in the first case, what are you doing to move from one term to the next? Adding 4, yeah? And what that hints to you is, oh, this has something to do with multiples of 4. If I'm adding 4 every time, that means it's 4 times something, yeah? And then you just kind of have to tweak around the edges to get it to work out. You're like, well, those aren't multiples of 4. Oh, but they're all 1 less than a multiple of 4. And the multiple of 4 I'm on happens to be the term I'm on. Does that make sense? The first one's 4 times 1 minus 1. Second one's 4 times 2 minus 1. It's just that's sort of how you think through it. So the first key is to kind of come up with, how am I moving from term to term? In the second case, you know, it was a little more straightforward. It was like, oh, the numerator and denominator, you kind of separate them out. In the third case, it was multiplying by -2/3 was the key. Just thinking about how many factors of -2/3 it took to get to like the 4th term or something. Just play around with like the first few, and then you'll probably discern a pattern, and then you can write down a general formula. And again, even like the ones with the factorials, how did I move from the 2nd to the 3rd term? I multiplied by 3 in the denominator. How did I move from the 3rd term to the 4th term? I multiplied by 4. Oh, excuse me. 2, 3, 4. That sounds like factorial if I were to take all those factors together. Does that make sense? Yeah. Yes.
I don't know if there's like a label for this function, but what if you have like x to the x versus like x factorial?
Well, let me show you something. So yeah. This is true. So in factorial, it turns out that this is really well approximated by n over e raised to the n times the square root of 2 pi n, which is sort of weird. But notice what's in here is an n to the n. Do you see that? And that's divided by e to the n. And then you have this thing that's just peanuts compared to the rest, but it's kind of an adjusting factor to make sure it all works out. But the factorial function does grow like n to the n, basically, is what this is saying. It's a little bit slower than n to the n, but it's pretty doggone close. N to the n would actually grow faster than the factorial function. This thing that I just wrote down right here is referred to as Stirling's approximation. If you try it out for various values of n, you'll see, man, this is like working really well, really fast. This is Stirling's approximation. By the end of this class, you'll actually have all the tools you need to understand why this approximation works. Okay, it's actually not very hard to see why. In fact, I wrote a little paper about it at one point, and it actually just talks about like very basic Calc 2 tools that actually help you understand why this is true. Right? But into the n actually beats a factorial. That's called super exponential growth. Super exponential growth is you basically have the base and the power growing at the same rate. Okay. Good question. Other questions? So, hey, can you guys look at these two things right here? Look at these two things right here and please discern for me whether they happen to converge or diverge as n goes to infinity, right? So I'm talking about taking the limit of those things as n goes to infinity. Do those things converge or diverge? So think about that for a couple minutes and then I'll ask for your input. All right, what have you got for me? Is there an initial simplification you can do with this thing, the log of n squared? What can I do with the 2? Yeah, so this is just 2 times logarithm of n over n. And if I let n go to infinity, what's the form of this thing? Yeah, so if I want to take the limit as n goes to infinity of 2 times logarithm of n over n, this is going to be, right, I'm going to use L'Hopital's rule, yeah? And we get the limit as n goes to infinity of 2, right? 2 just comes along for the ride, for sure. 2 times, what is it? 1 over n over 1. And so what do we get? Okay, 0. And that, my friends, is just exactly what I was talking about. What's the growth in the numerator in this case? What sort of growth is happening in the numerator? Logarithmic growth. What sort of growth is happening in the denominator? Polynomial growth. Logarithm is whipped by the polynomial, yes? In the hierarchy of growth rates, the polynomial is going to win. So it's not surprising that we end up getting 0 here. Does that make sense? What about this second guy? What did you guys do? No, did anyone try to do like some algebra first? Yeah. Why don't you find a common denominator? So like what's the common denominator? The product. Yeah, so 2n minus 1, 2n plus 1, 2n minus 1, which means I would have to multiply the first thing by 2n minus 1. Know what I'm saying? So it's like n squared times 2n minus 1 minus what? N squared times 2n plus 1. And what happens if I simplify that? Well, the 2n times n squared, those cancel, correct? And so what are we left with? Is it minus, okay, it's going to be negative n squared minus another n squared, which overall is how much? Negative 2n squared, and what's on the bottom? 4n squared minus 1, if you multiply that out. Okay? What does that go to as n goes to infinity? Okay, this is sort of shorthand for taking the limit as n goes to infinity. What do those terms go to as n goes to infinity? Negative 2 over 4, right? Negative 2 over 4. You could do L'Hopital's rule if you wanted to a couple times, but I'm telling you, negative 2 over 4 is what you're going to get. Right? It's the ratio of the leading terms here because the powers on n are the same in this case. Okay? So that's interesting. So that goes to negative 2 over 4. So both of these sequences converge. The first one to 0, the second one to negative 2 over 4, which is negative a half, of course. Okay. Any questions on that? Questions? I want to talk a little bit about this last part right here. Please, questions. Questions. I want to talk about this last part right here. And we'll explore this a little more carefully. Oh man, what am I doing? I'm zooming in. Okay, hang on. This. Okay, I want to at least introduce the notion of monotonic and what it means to be bounded above or bounded below. By the way, this little symbol that I'm writing here, this is just shorthand. What this means is for all. Okay, for all. It's just something that mathematicians like to use as shorthand for all. Okay. Monotonic. I mean, it sounds like some kind of drink or something, right? But monotonic means that the sequence is like moving in one direction all the time. Does that make sense? And look, you know what monotone means, don't you? I don't know if you've ever seen like Ferris Bueller's Day Off. There's like Ben Stein is this famous actor, and he's Bueller, and he's got this really monotonic voice, right? I mean, there's no like fluctuation in his voice whatsoever. It's robotic. Robot voices sound monotonic, or they're very monotone. So the word monotone has meaning, and in this case, it means that the sequence is always moving in the same direction, either in an upward direction as you go down the line, or a downward direction. Now, there's weird terminology that's used in the book, like non-decreasing. What? What does non-decreasing mean? It's always going up, but it leaves open the possibility of being equal at certain points. Does that make sense? So like non-decreasing means like A1, it can't ever decrease. It always has to be moving upward or staying the same. A1 is less than or equal to A2, is less than or equal to A3, is less than or equal to ... Now what about, so that's what monotone non-decreasing means. Okay. Now what about monotone non-increasing? What's that? Non-increasing means it can't increase, which means it's allowed to decrease or stay the same. Okay. This is like A1 greater than or equal to A2, greater than or equal to A3, greater than or equal to, etc. Right? So is it clear what monotonic means? That means moving in the same direction. Okay, either in a non-decreasing or a non-increasing way. What if I just said increasing? What would I mean? Yeah, that's right. Increasing means strictly increasing. You can't even be equal. It's just always going up strictly. Yeah? What if I said eventually increasing? Eventually, like it might horse around for a while, but eventually it's going up. Or eventually non-decreasing means eventually it's monotonic in a non-decreasing way, like from some point onward. Okay? So far, so good? Next, I want to say, I just want to introduce these things and we'll talk about them in more depth next time. A sequence is bounded above. Remember that we use that notation for sequence. We use the curly braces AN, yes? That means sequence AN. A sequence is bounded above if there's some number that's kind of like the ceiling for all the terms, yes? So it means AN is less than or equal to some number. They use U here. Why do you think they use U? Because it's called an upper bound, yeah? So all the terms are like below some number. There's a ceiling. So bounded above means there's some number that's serving as a ceiling. It's like all the numbers are below 5, for instance, yes? And of course, if they're all below 5, they're also all below 7, yeah? So if they have an upper bound, there's going to be lots of potential upper bounds. In fact, infinitely many upper bounds, yeah. Sure, you could say that. You could say bounded 5 serves as an upper bound for this sequence, okay? Now there's some like philosophical musings that happen where you start talking about, okay, if there is one, is there a least one? Is there a smallest upper bound? Does that make sense? Like 5's an upper bound, but how do I know I can't like sneak down a little bit more or something, right? And it turns out that that's a deep question actually. So existence of least upper bounds, and existence of greatest lower bounds, that's a deep sort of analytical, mathematical, philosophical question. Yes. Yeah. Yeah, a lot actually. I mean, in order to prove lots of things about convergence, you need to know stuff about, about.
I mean, like, could we get the upper bound less?
Yeah. That question, it does have practical application, yes. So by the same token, bounded below means that there's a floor below which nothing goes in the sequence. And that's called a lower bound. These are very intuitive terms, I hope, right? And what if I just flat out say that a sequence is bounded? What do I mean by that? It's between a floor and a ceiling. Like the entire sequence lives between some floor and a lower bound and an upper bound, yes? What we're going to talk about next time is what happens if I have a bounded monotonic sequence. Turns out that a sequence like that will have to converge, okay? It has to converge. But that's a question we'll look at next time, okay?